only makes sense for graphics, but then there has been a lot of hype with GPUs. Do you see any other application domains where GPU
looks like graphics will work well on GPUs because GPUs are optimized for graphics? What I don't see is I don't see people putting GPUs in machines if they're not doing graphics. And you will have devices like, my laptop is always going to have a GPU because I need graphics, and I can use that GPU for other things that are graphics-like efficiently. But if they're not graphics-like programs, it's not going to work so well on the GPU. And if I have a machine that isn't doing graphics, I'm not going to put a graphics processor in it. That's my take.
Yep, go ahead. You can speak up a little bit.
When I'm rebuilding a Linux file system, I have a program that runs around 8,000 tasks. It takes 6 hours to run. Do you know if anyone is trying to run on the CM5, for instance, the C compiler?
So the question is, has anybody been running things like a C compiler on Xeon Phi? And the answer is you can run whatever you want on that. If you have a C compiler, which will spawn a whole bunch of tasks, you can absolutely run it there. The issue with compiling in particular is an interesting one because you have a lot of time spent doing disk I/O. And Xeon Phi doesn't really have a disk. So you'd be going over PCIe for that and you'd have problems with communication there. Now, if you were able to transfer all of your data to it before you did it, then you might be able to get great speed-ups. But this is exactly what Intel is betting on, that because you can just press run and recompile your code, you don't have to rewrite it, people are going to find all sorts of other uses for that.
One last question of Stefanos.
So Stefanos' question was basically, we get GPUs in scientific computing and everywhere else for free because the video gamers subsidize their development. And that is absolutely the case. This is both a good thing and a scary thing. So it's good in that we do get them for free, but it's also a scary thing because gaming is moving entirely mobile, and you didn't see NVIDIA or AMD on that graph I showed you for the mobile market. So I don't have a lot of faith that they're going to be relevant players in the next 10 years. But the bigger issue here is that GPUs in scientific computing are mostly limited, or any sort of computing, by the fact you have to rewrite your code. And if they can't get over that part, it's just too expensive to adopt them. And if Intel can be successful in making it easy to port, that's a huge win for them.
Thank you. I think we have to cut the questions there. So there was somebody over here as well. But please catch David. He's going to be around here for at least the beginning of the afternoon as well. Thank you. So it's my great pleasure to introduce Keshav Pingali. Keshav got his PhD at MIT, working on data flow and functional languages. And I had the opportunity of visiting there for 1.5 years in the 80s. And that's the first time I saw parallel processing and first time I got excited in the subject. So that's partly thanks to Keshav and his people there, so Professor Arvind and others in that group. That was the first time I met Saif as well, actually. He moved on to Cornell University, and he's now at University of Texas. He has a chaired professor there. And as you understand, he has been working on parallel languages for a long time, going all the way back to the pioneers. So please, Keshav, it's good to have you here.
Thank you. Is this about right? Okay, can you hear me? Good. Well, thank you, Eric, and thank you for coming this morning. As we all know, parallel hardware is everywhere. Even 10, 15 years ago, the only place where you'd find parallel hardware, it was in these high-performance computing centers, like the one that we have at the University of Texas at Austin.
So it's called TAC for the Texas Advanced Computing Center, and we have one of the biggest distributed memory machines in the world over there. And 10, 15 years ago, that was about the only place where one would find parallel hardware. Then what happened was that increasingly laptops, desktops, and so on started to have parallel hardware inside them, so you had multi-core processors. And so that picture in the middle shows you a few Swedish girls in a school who are sitting there doing something on their laptop. But even laptops are fairly expensive devices, and so what has happened more recently is that, does this work? Good. What has happened more recently is that we now have cell phones, and cell phones increasingly are parallel computing platforms. And so the bottom picture shows you a lady in India who's calling somebody on her cell phone. And if you look inside the Snapdragon platform, for example, what you find is parallel hardware again, a multi-core device with a few GPUs inside it. And so parallel hardware really is ubiquitous. It's everywhere. So you would think that parallel programming then is also ubiquitous, that it's become very simple and it can be used everywhere. Unfortunately, that's not quite true. Even though there's been roughly 40 to 50 years of work, even though there's been more than 40 to 50 years of work on parallel computing, for the most part, the kind of programs that people know how to parallelize well are really in the high-performance computing domain. So the kind of programs that you would run on these large distributed memory machines, like the ones that we have in Texas. The kind of programs that run there are what in the compiler community we call regular programs. So for the most part, they focus on matrix and vector algorithms. So stencil computations or finite difference computations are a good example of that. Similarly, FFTs and so on and so forth. And the characteristic, as I will tell you later in my talk, of these kinds of regular applications is that you can build a dependence graph before you run the program for the computations that you need to do, and then you can schedule at runtime according to that dependence graph. There's a very mature theory at this point that tells you how to think about parallelism in these regular applications. There are also a lot of robust tools, compiler tools, runtime systems, and so on and so forth that people use fairly routinely. Unfortunately, it turns out that the kind of programs that that lady is likely to be running on her cell phone, so things like web browsers and Google searches and so on and so forth, don't really fall in this nice, simple, regular category. Instead, they are what in the compiler world we call irregular programs. For a long time, irregular simply meant we don't know what to do with them, right? But one way to think about irregular algorithms is that they use far more complicated data structures. So data structures like graphs and sets and priority queues and so on and so forth. So these are far more complicated than these regular algorithms. And it turns out that the techniques, the tools, the theory, and so on that we've developed over the last 40 years for parallelizing these matrix vector algorithms don't really work for these far more complicated irregular algorithms. In the last 5 years or so, in my group at the University of Texas, we've been developing a general framework, a way of thinking about parallelism and locality that's general in the sense that it captures the parallelism and locality patterns that you find, both in these irregular algorithms as well as regular algorithms. So regular algorithms turn out to be a special case of irregular algorithms in a way that I will make clear as we go through my talk. Not only is this a framework, but we also have built a system for both multi-cores and GPUs. And so I'll show you some performance numbers that show you that you can really get very good performance if you program according to this data-centric approach, which is what I'm going to push today. Here's a one-slide summary of what we have learned in the past 5 years. And so I call it yesterday and today, the way we used to think about some of these issues even 5 years ago, and the way that it has changed today. So we have learned a number of things in many areas: algorithms, abstractions for parallelism, how do you think about parallelism in those algorithms, parallelization strategies, as well as how one writes applications. So even 5 years ago, we used to make this distinction between regular and irregular algorithms. algorithms that I mentioned in the last slide. So regular algorithms were these nice matrix and vector algorithms that we know what to do with. Everything else we put into this category of irregular algorithms. Today, our view on that has changed. There are just algorithms. Some have more structure than others. And so this has unified these otherwise seemingly different worlds. In the same way, for a long time, we used to make a distinction between sequential algorithms and parallel algorithms. But today, again, our view on this has changed. What we realize today is there are just algorithms. Some have more parallelism than others. So again, there is a certain unification that's taken place in the way we think about algorithms themselves. How about abstractions for parallelism? For a very long time, the way we thought about parallelism was in terms of what I'm going to call computation-centric abstractions. So what we were told to do was to look for loops or procedure calls that we could do in parallel. So you took the text of the program and then you looked for parallel constructs, like loops inside those. Instead, what I'm going to argue is that you need to think about parallelism in a very different way. I'm going to call it a data-centric way of thinking about parallelism. What you do is you think about data structures and you think about operations on your data structures. And so it's the data structures that take the center place rather than the program. So in particular, I'm going to talk about something called the operator formulation of algorithms, which is a way of thinking about the algorithms in this data-centric way. And it turns out if you do that, then it gives you a very simple way of thinking about parallelism in all kinds of algorithms, both regular and irregular, sequential and parallel. Our view of parallelization strategies has also changed. So the way we used to think about parallelization 4 or 5 years ago is that static parallelization is the norm. Given the algorithm, given the program, either you or a compiler would build a dependence graph and then you would schedule according to that dependence graph. We were, of course, aware that there were things like speculative execution, but the feeling was that those were for some weird programs that you don't really understand, and that if you really understood what you were doing, you don't really need all these other parallelization strategies. Today, our view on that has changed, so I'm going to argue that actually speculative or optimistic parallelization should be the baseline, and then things like static parallelization, where you can actually build a dependence graph at compile time, is possible only for some very special algorithms that have enough structure that you can do these parallelization decisions at compile time. And then finally, the way we think about applications has also changed. So 5 years ago, we used to think about programs as these big monolithic entities. And in the compiler world, at least, we would talk about doing whole program analysis, where we would read in the entire program, build a big interprocedural control flow graph, propagate information all around, and so on. Today, what we realize is that programs must be layered. So data abstraction is essential, not only for software engineering, but even for parallelism. So a lot of these things are fairly abstract, and what I'm going to do in the rest of my talk is to tell you about each of these points. So the best way to understand these things is to take an example. And so I'm going to take one example over here, which is an irregular application. So here is the way we used to think about parallelism even 4 or 5 years ago. So I give you some pseudocode, the pseudocode on the left side of my slide, and then I want you to parallelize it. Now, if you say, well, what does that program do? Well, we were told it doesn't really matter what the program does. After all, computer architectures don't know anything about algorithms, so why should people who are thinking about parallelism know anything about algorithms either? It's just a program. So, well, then how do you parallelize it? Oh, look for loops. Well, there you go. There is a loop over there. There's that nice while loop. And so the way we thought about parallelization was you take that while loop and then you try and build a dependence graph for the iterations of that loop at compile time. Now, there were very fancy, complicated techniques for doing that kind of analysis called shape analysis that people found in the compiler world. But what all of these analysis techniques did was when they analyzed a loop like that, they wouldn't find any parallelism. They would come back saying that all the iterations were really dependent on each other, and therefore you were compelled to execute this program in parallel. So that led to two different schools of thought. So one school of thought said, well, maybe that means there is no parallelism in these kinds of applications, so that's why your tools are not able to find any parallelism. The other school of thought said, well, maybe your analysis techniques are not sophisticated enough, and so what you need to do is to write research proposals, to raise more money, to do more analysis work, so the usual academic racket that we're all involved in. Now, there were also other techniques, like thread-level speculation that people tried with these kinds of programs. So in thread-level speculation, you just speculatively start executing these iterations in parallel. If you find conflicts, you roll back, and so on. But for reasons that I don't have time to go into, it turns out there's a lot of misspeculation, and the overheads of the thread-level speculation, the way it used to be done, basically limit any performance advance that you get from that particular strategy. Moreover, there was a belief that misspeculation costs power and energy. After all, in a world in which power and energy are important, the fact that you have misspeculations, the fact that you're actually doing unnecessary work, you're trying to do work in parallel, failing, rolling back, and so on, well, misspeculation costs power and energy. Therefore, this kind of thread-level speculation was actually a bad idea, or so we thought. Today, we think about the same program in a very different way. So here is how I want you to think about it, and this illustrates this data-centric way of thinking about the algorithm. What that algorithm does is something called Delaunay mesh refinement, and I'm going to describe it at a very high level to you. The input to that algorithm is a mesh of some kind, so it's a mesh of triangles. Some of these initial triangles are badly shaped according to some shape criteria that we don't need to worry about. Those are the ones that are marked in red. And I'm going to call those bad triangles active elements. So you should think of them as flashing red in the mesh, saying, some thread, please come over here and fix me because there is something wrong with my shape. Okay? Now, the way that that's done is by refinement. And let me see if this demo works, and otherwise I have a backup. Okay, that didn't work, so let's go to okay, so there is an initial mesh. Some of those are badly shaped triangles, the ones in red. So the way that the refinement works is you pick any badly shaped triangle, like the one that I selected over there, and you replace it with smaller triangles. But if you only do that, then it turns out that some geometric constraints that all triangles need to satisfy, called the Delaunay condition, which again we don't need to worry about, may be violated for some of the triangles surrounding that bad triangle. So what you actually do is you find all of the affected triangles that are said to lie in the cavity of that bad triangle, and then you replace all of them with new triangles. Some of these new triangles may themselves be badly shaped. Well, that's fine. You just keep going. And if I just run this for a little while, you end up with a mesh, and all of you must have seen meshes like this at some point or the other. Well, this is one algorithm for producing these kinds of meshes. So I'm going to turn this animation off because I find people are just focused totally on that and ignore what I say. So let's go back. That's right. Okay, so now that you understand what that algorithm is, I want to think about it a little abstractly. So I want to think about the bad triangles as active elements. So they're sort of flashing red over there saying, some thread, please come and fix me. The computation that you do at an active element is what I want to think of as the operator. So the operator is that unit of computation that gets done by the algorithm at an active element. And so for this particular algorithm, it's basically find the cavity of that bad triangle, remove those triangles, replace them with new triangles, etc. So the way that I want to think about the algorithm is in terms of what, where, and when. So what does the algorithm actually do? Well, that is the operator. Where does it do that particular computation? That's at the active elements, in this case, the bad triangles. And then in general, you're going to have multiple active elements. You're going to have many bad triangles. And so I need to give you a schedule, even for a sequential implementation, in which you're going to do all of those bad triangles. So it turns out the way you want to do that is in LIFO order. You want to maintain a stack, because when you process a bad triangle, you might create new bad triangles. You want to push them on the stack and work on them right away, because then you have good locality. And so if you use a stack as opposed to just randomly picking bad triangles to process, you get a speed up of 2 even on a sequential implementation. Okay, so I think about the algorithm in terms of what, where, when. Operator, active element, and schedule. How do I think about parallelism in this data-centric model? Well, the moment you have multiple active elements, obviously you can have multiple threads coming, each one working on a different bad triangle. As long as the cavities don't overlap, you can obviously process them in parallel, and everything is fine. This parallelism, you obviously cannot find at compile time, because you can process triangles in parallel only if their cavities don't overlap, only if they're far away in the mesh, and that's not something that you can detect at compile time. So fundamentally, some kind of runtime parallelization is going to be required, and different schedules have different amounts of parallelism and locality. To show you that this is a very general way of thinking about parallelism, let's take a different application, this time from the world of graph analytics. So this is the single source shortest path problem that I'm sure all of you are familiar with. So this is one of the first problems, one of the first algorithms that all of us learned in an introductory algorithms course. So the way the problem is stated, you're given a graph of some kind, which is an undirected graph. The edges have lengths or weights on them. And the nodes, for example, so this might be a road map. The nodes might represent cities. The edges represent roads with certain distances. One of the nodes is called the source. And then what you want to do is to find the length of the shortest path from the source to each of the other nodes in the graph. And so in this case, I've picked A as the source, and its distance from itself is 0, and all the other distances are initialized to infinity, because initially you don't really know how far each city is from the source. Now, there are many algorithms for the SSSP problem. So you have Dijkstra's algorithm, Bellman-Ford, chaotic relaxation, delta stepping. So I'm sure all of you have seen at least one or more of these algorithms. And if you look at it in textbooks, they're presented as though they were totally different algorithms unrelated to each other. If you look at it in data-centric terms, in the way that I was talking about in the previous slide, there's a nice, simple, uniform structure that emerges. It turns out that what all of these algorithms do is to essentially keep successively updating these labels at these nodes. And so these labels keep moving down. And when all the labels settle down, that gives you the solution to the single source shortest path problem. What is the operator? What is the unit of work? So that is the relax edge operation. Essentially, what you do is you look at an edge. You look at the current distance from the source to this one, and then you add the weight of the edge. So if you have an edge UV, you take the current label of U, you add the length of the edge to it, you see if that is less than the current label of B. And if so, you update that distance field. So if I were to relax the two edges going out of A, I would get this situation where I have this label relaxed to 2 and this label relaxed to 5. Okay, so that's the operator. So what is an active node in this algorithm? An active node is any node whose distance label has been lowered, but you have not yet looked at its neighbors to see if you can relax them too. The remaining thing is the schedule, and this is where the different algorithms differ. So in chaotic relaxation, you're allowed to apply the relaxation operator anywhere where you can. And so if this is the current situation where B and C are active, you're allowed to relax the edge BD, so then that lowers D to 12. And then you can relax the edges going out of 12, so then you propagate some information into the subgraph over here. At some later point, you relax C, and so then D gets lowered to 3, and then you propagate information again into that particular subgraph. And so what's going to happen over here is you're going to visit nodes a lot of times, and so chaotic relaxation has lots of parallelism. However, it turns out that you don't have very good work efficiency. If you want good work efficiency, you need to process these active nodes in increasing distance order. That's what Dijkstra's algorithm does. And delta stepping and Bellman-Ford are just different schedules. And so what happens is these seemingly different algorithms essentially end up looking quite uniform. All of them have the same notion of active nodes. They have the same operator. What's different about them is you use different schedules. And these schedules make a difference in this algorithm in parallelism, locality, as well as work efficiency. The last example I want to take to show you the power of this data-centric way of thinking about it is stencil computations. So this is what we call a regular algorithm. We know how to parallelize this statically, but it turns out even this is, it's useful to think about parallelism in this algorithm in a data-centric way. So this is your classical finite difference computation. So what you're given is an initial grid in this case. So that's A sub t, and you're solving something like the heat equation. So you have some initial values at each of those grid points. And then the way that you compute the values at the next time step, A t plus 1, this grid over here is, you update this point by taking the weighted average of the immediate neighbors at the previous time step. So again, if you were to analyze this algorithm in our data-centric terms, here is where are the active nodes? Well, they're all the nodes in A t plus 1. What is the operator? Well, the operator is that 5-point stencil. And then you can have different ways of visiting the points in A t plus 1 to update them. In this case, the amount of parallelism and work efficiency is the same for all schedules, but the amount of locality is different. So again, you'll get different amounts of performance. Now, in this application, the grid structure and the active nodes are all known statically. The only thing that I don't know at compile time is the size of the grid, but otherwise I know everything about the active nodes, the neighborhoods, and so on. So this application can actually be parallelized at compile time. So when you know the active nodes and neighborhoods at compile time, you can do static parallelization. What that means is I can take the text of the program and then in the classical way, look at those loops, parallelize the loops, et cetera, et cetera. But that's only because this particular application is very restricted. It's because you know the active nodes and neighborhoods at compile time, which we didn't know for the other applications that we considered previously. At this point, let's put it all together now and talk about this general abstraction that I want to use for thinking about parallelism in algorithms. So this is this operator formulation. Rather than think in terms of loops and computation structures and trying to find parallelism that way by looking at the text of the program, I want you to think in terms of looking at the data structure and then these actions or updates on the data structure. So I've taken a general graph over there. So there is a notion of an active element in all of these algorithms. So those are sites in the graph where there is some work that needs to be done. The work itself is what we call the operator. So that's the computation that's performed at the active element, and an activity is simply the application of the operator to the active element. In general, an activity is going to read and write not only the active node, but some small region around the active node. So we call that the neighborhood for this particular activity. That's a set of nodes and edges read and written by this activity. It's usually distinct from the neighbors in the graph. And then the only other thing that you need to remember is the ordering. So in some algorithms, when you have multiple active nodes, even in a serial implementation, you're allowed to process these active nodes in any order at all, although different orders, different schedules make a difference as far as the amount of locality and work efficiency goes, as we saw in the SSSP example. So these are what we call unordered algorithms. And in other algorithms, there is some problem-dependent order in which the activities must appear to have been done. So if you know discrete event simulation, that's an example where there is a problem-dependent order in which the activities must appear to have been done, and that's what we call ordered algorithms. So how do I think about parallelism in this model? Well, this is what we call amorphous data parallelism. It's a generalized kind of data parallelism where you're allowed to process multiple active nodes in parallel provided you respect these neighborhood constraints. So if two neighborhoods overlap, well, then you can't do those activities in parallel. But if they don't overlap, then you're allowed to do them in parallel, subject to whatever ordering constraints there are in your algorithm. So here's the motto that I want you to take away from this discussion. The way I want to think about a parallel program now is not in terms of do all loops, et cetera, I want you to think about it in data-centric terms. So a parallel program for us is an operator plus schedule and a parallel data structure. So for example, you need a data structure to keep track of all the active elements that you have that different threads can come and take from. So I need to give you parallel data structures, and then if I specify the operator and schedule, that's essentially the way you think about a parallel program. Eric, what time do I need to end? 11:30.
We need time for questions at the end as well. So,
Good.
And if you go into 15 past now.
Okay, very good. Okay, so that's the operator formulation of algorithms. This is the way I want you to think in data-centric terms about algorithms. And now there is a very simple analysis that you can do of algorithms that exposes the structure that's present that you might be able to exploit. So we call this the tau structure of algorithms, and it stands for topology, active nodes, and operator. So topology refers to whatever structure you may have in that graph. So for some applications, like single source shortest path, you just have a general graph, and there's no particular structure over there. So that's what we call unstructured. It's just a general graph. But for the finite difference or stencil computation, we saw that that graph was actually a grid. A grid is a very special graph where there's a lot of structure. And if you know at compile time that you have a grid rather than a general graph, you obviously may be able to exploit that for efficiency. And so you have structured topologies, and then in between you have trees, which we call semi-structured. So that's the topology of the data structure itself. Then there is structure in the active nodes. So where are the active nodes located, and is there any order in which these active nodes should appear to have been processed? So when it comes to location, we have two classes of algorithms. The algorithms like single source shortest path or Delaunay mesh refinement we call data-driven because elements become active in a very unpredictable, dynamic way. So those are called data-driven algorithms. And then you have things like the stencil computation where we said all the nodes in the grid are active, and then you just process them. So those we call topology-driven algorithms. And obviously, topology-driven algorithms are simpler because once I give you the graph, you immediately know all the active nodes. Whereas in a data-driven algorithm, things are becoming active dynamically, so you have to do more things at runtime. The final dimension is the operator. So the most general operator is like the Delaunay mesh refinement operator. It's allowed to modify the graph structure by adding and removing nodes and edges. Those are the most complicated ones because the underlying data structure must allow you to add and remove elements in the representation of the graph. Local computation is what you do in graph analytics. So in graph analytics, you don't modify the graph structure, you just update labels on nodes and edges. So that's what we call local computation. And the reader doesn't update anything in the data structure, it's only read-only as far as that data structure is concerned. And so now you can take the algorithms that we talked about and classify them along these dimensions. So let me just take Delaunay mesh refinement, and I'll leave the rest of them for you. So obviously that operates on a general graph. It's a data-driven algorithm because bad triangles are being created dynamically on the fly. It's unordered because you can do them in any order at all. And then the operator is a morph. For Jacobi, you have a grid. So that's a very structured topology. It's a topology-driven algorithm because once I give you that grid, all of the elements are active. So you know all the active elements. As soon as I tell you the graph, it's unordered, and it's local computation. Now the question is, when can I make the parallelization decisions? In the old way of thinking about it, you made all your parallelization decisions at compile time. You built that dependence graph, and then that told you, how to schedule things in parallel. Well, here we need to worry about what we call binding time. So you can take parallelization decisions when you know the active nodes and neighborhoods. And there's really an entire spectrum of times when you know active nodes and neighborhoods, depending on the algorithm. So in the simplest algorithms, you know the active nodes and neighborhoods at compile time. So things like stencil codes, FFTs, dense linear algebra, and so on. So for them, you can do all your parallelization decisions statically. In the most complicated case, you only know the active nodes and neighborhoods after the program has finished. And so for those, you need speculative execution. So time warp way of doing discrete event simulation is an example of that. And then it turns out there are also intermediate points when you can figure out the active nodes and neighborhoods. So the inspector-executor approach that some of you might know, well, you know the active nodes and neighborhoods when the input is given to you. At runtime, you examine the input. That tells you all the active nodes and neighborhoods. So you can make the scheduling decisions at runtime, but before you actually execute the algorithm. And so the Bellman-Ford algorithm for single source shortest path is an example of that. The next question is locality. Is this data-centric way, this operator formulation, useful for thinking about locality in algorithms? And again, it gives you a lot of insight. So temporal locality, for example, what it says is if you have activities that have overlapping neighborhoods, those should be scheduled close together in time on the same core because their working sets are going to overlap and you get good locality. So this was that stack schedule that we use for Delaunay mesh refinement, for example, which is the best schedule if you're doing a serial implementation. So it would say, for example, that activities I1 and I2 should be scheduled together on the same core, one after another, because their working set overlap. There's also spatial locality. For spatial locality, you need to look at the representation of the graph. So not at the abstract data type, but at the concrete data structure that's backing up that particular abstract data type. So here is one way of representing a graph. You just list all of the edges in sequence, the source number, source node, destination node, the value on that node. And so this tells you the order in which edges should be processed if you want good spatial locality. And then there's also inter-package locality because current multi-core processors are actually NUMA. And so the way to think about that is you partition the graph between packages, and then you also partition the concrete data structures appropriately, and then the active node is processed by whichever package happens to own that particular node. And so this operator formulation of algorithms also gives you insight into how to think about locality, which, as you know, is extremely important, as important, if not more important, than parallelism. Let me skip over that. And so now let me tell you about our system. So far, what I've been telling you about is a data-centric way of thinking about parallelism and locality in algorithms, where you don't look at the text of the program, rather you think in terms of data structures and then these actions or updates on these data structures. And so you might be wondering, well, okay, this is a theory. Is it good for anything? What are we going to do with it? What we've done with it is to actually build a system that we call the Galois system, where we write programs in this data-centric way, and then we run them on multi-cores and GPUs. This is our contribution to ubiquitous parallelism. So what is ubiquitous parallelism? I think the only way that multi-cores, multi-core programming is going to become widespread is if you have a small number of expert programmers, which for various reasons we call Stephanies, get to support a large number of application programmers who don't have to write explicitly parallel code in order to exploit the multi-core or GPU parallelism. Now, this might seem like a very ambitious goal, and it is an ambitious goal, but I believe this particular approach, this division of labor between expert parallel programmers and application programmers who don't have to write explicitly parallel code, is responsible for the success of SQL. So a lot of people say SQL is the world's most successful parallel programming language. How does that work? Well, you have a small number of expert programmers at IBM, Oracle, and so on who build these relational database systems. And those are very complicated systems. You have transactions and B trees, concurrent B trees, and all of these other horrible things that we use to torment our graduate students with in their qualifying exams. And then the vast majority of people in the world who use these database systems just write SQL programs. There are no threads, no transactions, anything. It's a mostly functional language, and that is translated into code that runs on your database system. And there are millions of people in places like India, for example, who make their living writing these SQL programs using parallelism very successfully without really knowing a whole lot about concurrency control and so on and so forth. I believe this is the only way in which multi-cores are going to succeed, multi-core programming. And so our system is designed along the same lines. And so here is what we do. In our world, we divide our work into algorithms and data structures. And so this is program equals algorithm plus data structure, which was Nicolaus Wirth's famous motto. So for us, a parallel program is an operator plus schedule. That's how you specify the parallel algorithm. And then you have the parallel data structures. So in the Galois system, what we give you is a library of concurrent data structures written by expert programmers, so my graduate students. And then applications are just built on top of that. They're written in sequential C++, and all of the concurrency control is done within the data structure library and in the runtime system. So when you write an application like Delaunay mesh refinement or single source shortest path or any of those other applications that we took, in the application code it's just sequential C++, but you invoke the methods of our data structures, and all the concurrency control is done within that data structure code. The application code itself has no notion of threads, locks, or anything else. And then what the runtime system does is it basically executes these activities asynchronously. So there is a bag that's built of all of your active nodes. That is one of the data structures that we give you, a concurrent bag. So your active nodes are all populated in that bag. Different threads will come, pick these active nodes out of the bag, and then asynchronously they start executing. If there are conflicts, those are detected within the concurrent data structure, rollbacks, etc. All of that happens automatically. If you have static parallelization, well, then we build the dependence graph, etc. So all of those things are transparent to you. But what you need to tell us for specifying your algorithm is the operator and the schedule. And you do that just by writing sequential C++ code. And then you have to use our data structures. That's the big restriction that we have currently. You have to use our data structure library. OK, so how well does this do? So here are some numbers on a very large NUMA machine. So this is the SGI Ultraviolet. That's at the University of Illinois, Urbana-Champaign. So it's a big NUMA machine. It's got 512 cores. So the x-axis is just the number of cores on which you're running your application. And then the y-axis shows you scaling. So single-threaded performance, so the time to execute your application on one thread divided by the time to execute it on however many threads you want to run it on. And the different lines over here show you the scaling for different applications. So Delaunay mesh refinement, which was that complicated mesh refinement example we took, as you can see, you get a scaling of about 420 on 512 cores. Okay, now remember, this is Joe code. There are no threads, there are no locks, anything of that sort. It's just sequential C++, and it's invoking our library data structures. And
who writes the Joe code? Who's Joe?
Joe is any application programmer. So for example, if...
Do you think somebody from the street who's doing this? Or?
Right now, it's not anybody from the street, but it's other students in my group. And so what we found is that there is actually a big difference in the skill sets even of my own graduate students. So there are a couple of students who are absolutely superb master hackers, right? So there are our Stephanies. And then the vast majority of my graduate students, or we've also used this in my courses, they really don't have the skills to do a good job of parallel programming. So what I ask them to do is to implement these different applications using the data structures and the runtime system that has been written by the two Stephanies that I have. That's all you need. And neither of them is called Stephanie, but Andrew and Donald. OK, so that's Delaunay mesh refinement, and you can see that's giving you reasonable performance. Let me just talk about one other application. So this is triangles. So this is, given a graph, you want to know how many triangles are formed by 3 nodes. And this is a simple benchmark that lots of people are using in the machine learning community. And so as you can see, for that we get a scaling of about 256. Now, those of you who know anything about parallel programming know that scaling can be cheating, right? Because you don't really know how bad your single-threaded performance is. And so one always has to talk about comparing it to somebody else's highly optimized sequential code, et cetera, et cetera. And that's always hard to do. But we have done some of those comparisons. And so I want to show you 2 examples of that. For Delaunay mesh refinement, there is a code called Triangle from Jonathan Shuchak at Berkeley. So he's a computational geometry guy who spent a lot of his career doing mesh generation, mesh refinement, and so on. He has highly optimized C code, sequential. So for this particular input, it takes 96 seconds. Our code on one thread takes roughly twice as much time. And that's because it's a parallel code and it's still doing all the underlying locking and thread management and so on. But what you can see is at 512 cores, it goes to about 0.37 seconds. And so you get a speed up of about 300 compared to somebody else's highly optimized sequential C code. So this is genuine performance. Okay? The other application I want to show you is this triangle application. So in the machine learning community, there is this package called GraphLab that has become extremely popular for running these machine learning applications. So on 2 threads, on one thread for this input, it didn't terminate. On 2 threads, it takes 531 seconds. A one-threaded program takes 7 seconds.
GraphLab is much slower.
That's right.
It's very well.
Even sequentially. That's right. And now you might wonder, well, why is it so much slower when what the computation that you're doing is the same? Well, it's essentially because we support a much richer class of schedules than they do. So they have some very simple schedules. With those simple schedules, the work efficiency of their algorithm is quite poor, whereas we can support very sophisticated schedules, and so the work efficiency is much better in our implementation. And you can see this even in single source shortest path, because if you use chaotic relaxation, it can take thousands of times longer than if you used a good schedule like delta stepping. So it's all about schedules and the richness of the schedules that you can support for doing these activities. And what you notice is on 512, we get about 0.028, and now you can do the division here. It's many, many orders of magnitude faster. Okay, so that's on the ultraviolet. I want to show you a very complicated application, which is called METIS. So METIS is a graph partitioner that lots of people use. I give you a graph, and graph bisection says, divide the graph into 2 subgraphs so that they have roughly the same number of nodes, and you minimize the number of edges that you've cut, and then you can do that recursively. So this is a program that's been around for about 20 years or so. It was developed by George Karipis at Minnesota, and lots of people use it on all these HPC centers. So here, what I'm showing you are a bunch of input graphs. Some of them are road networks, others are circuits, and so on. The y-axis is running time of different implementations, so lower is better. The red line over here shows you METIS time. So you just take sequential METIS, which is a highly optimized C code, and you run it. And for this particular input graph, which is Europe, so the road network, so it takes about 65 seconds. Okay. Now, let's forget about the green line. The blue line over here shows you our Galois version of METIS. So we studied their algorithms, and then we rewrote their code in our system in this data-centric way. So it's C++, you use our data structures, and then you specify the operator schedule, et cetera, et cetera. No, this one is on 24 cores. That's right. So I just give you 24 cores, and then we let our program run. And so what you notice is you get genuine speed up again. So you get about 8 seconds as opposed to 64. So you don't get perfect speed up. But on the other hand, what we are saying is you get roughly an order of magnitude improvement in performance right? It runs roughly 10 times faster than the sequential METIS that has been around for a very long time. So again, what this is telling you is, I'm not giving you scaling numbers and so on and so forth in order to impress you. I'm showing you genuine speed up with respect to somebody else's highly optimized C code for this very complicated graph partitioning problem. Is that clear? Okay. Now we also have GPU implementations, and so what you can do is use this operator formulation that I talked about, and you can use it to produce GPU code. Now this is not written in that C++ style that I showed you. Rather, what you do is you think about the algorithm in terms of the operator formulation, and then you translate that more or less in a straightforward way into CUDA code. So this is actual CUDA code for a number of these very complicated applications. So here is Delaunay mesh refinement again. So remember, this is that mesh refinement. It's modifying the mesh. So it's really a very complicated application. You don't really think of that as being very GPU friendly. But what it shows you over here is our multi-core implementation running on 16 cores. So that is the blue line over here. And as you can see, our multi-core implementation does quite well. The red line over here shows you the performance on one NVIDIA Tesla. And so what we're telling you is, even these highly irregular algorithms, where the graph structure itself is constantly changing, well, even those we can actually implement in a more or less straightforward way on GPUs and get good performance over there. And then these other charts over here show you other applications. This one is points to analysis. So there is a very complicated points to analysis. It's a kind of analysis that's done within LLVM, GCC, and so on. So it's part of optimizing compiler. And so we were able to produce the first GPU implementation of points to analysis. And as you can see, even on that very complicated compiler analysis, which you don't really think of as being very GPU friendly, we actually get good performance. The last set of numbers I want to show you are going to appear in SOSP next month. So that's the Symposium on Operating Systems Principles. So this graph analytics has become a very hot area. And so what we decided to do was the following experiment. There are a bunch of graph domain-specific languages that people have come up with for doing graph analytics. So one called PowerGraph, which is essentially the son of GraphLab, and Ligra, which Guy Blelock at Carnegie Mellon has come up with. So these are domain-specific languages for writing these graph analytics applications, like that single source shortest path and other applications. So we thought, well, let's take a look at how well we do for those applications. So there's a lot of data over here, but on this axis, I'm showing you different graph analytics applications. This is single source shortest path. This is PageRank, finding the pseudo diameter of a graph, breadth first search, connected components. So we take different applications, and then we said, let's write them in the Galois system. So we're allowed to use whatever schedules we are good for these algorithms. And then we'll take the Ligra implementation and the PowerGraph implementation, and we'll see who's faster. Okay? So the y-axis over here shows you the running time of Ligra divided by the running time of Galois, and similarly running time in PowerGraph divided by the running time of Galois. Now, usually we tell our students to say higher is better, lower is better, etc. But in this case, well, you're comparing two running times. So higher is better for Galois because it says the running time is smaller. And what you can see is in most of these applications, if you look at the running time in Ligra divided by the running time in Galois, it's between 1 and 10 times faster in our system. When it comes to things like PowerGraph, well, we're actually factors of 1,000 faster for this particular input, which is the Twitter 50 input. It's a social network graph. For road applications, which is a large diameter graph, the factors are in fact 1,000 to 10,000 times faster. So again, same number of CPUs. That's right. And so again, if you say, where's the magic? The magic essentially is we can support much more sophisticated schedules than they can in these DSLs, and that's what lets us run orders of magnitude faster. Now, the other thing that we did was we said, let's take Galois and then implement a thin layer on top of it to support these DSLs directly. So you can take their applications with their schedules, etc., and then run them on top of the Galois system. So now everybody's using the same schedule. And if you see an improvement when you run it on our system, it's because our system is better instrumented, it's better built. And so here the improvement is not as impressive, obviously, because we're using the same schedule as they are. But again, what you notice is there are sometimes factors of 50 faster, even when you're looking at the same schedules. And so the takeaway message over here is that we can use Galois as a lightweight infrastructure for doing graph analytics, and it does very well compared to custom-built DSLs like Ligra and PowerGraph, which are intended for graph analytics. Let me skip over this and just talk about relationship now to other parallel programming models. And so this is the motto which I wanted you to take away for the Galois system. So parallel program is operator plus schedule plus parallel data structure. And the operator itself you can think of as an update or a graph rewrite rule on data structures. You can connect this to the way that people have been thinking about functional languages. So a lot of people have proposed functional languages as a parallel programming paradigm. The semantics of functional languages are specified in terms of rewrite rules, like the beta reduction rule for lambda calculus. So you can think about that as the operator in their case. What is the schedule? The schedule over there is things like application order, normal order reduction, and so on and so forth. So in the functional languages world, they have explored a bunch of different schedules for implementing functional language programs. But remember that we use our updates to update data structures, not the text of the program, the way you think about it in functional languages. But there is a connection to this operator plus schedule idea. There's also a lot of interest in transactions and transactional memory. So again, there is a connection. Each activity in Galois has transactional semantics because it either executes or else it rolls back and it's as though it never happened. And so we have atomicity, consistency, isolation, etc., etc. But the way you think about transactions, they're a synchronization construct for an explicitly parallel threaded programming model, whereas the Joe programming model for Galois is sequential. So there's no notion of transactions anywhere in our code, but it's just that each activity has transactional semantics, and that's enforced by the underlying system. But if you like transactions, well, that's the connection to that. And then there's also a connection to BSP, or the bulk synchronous model, but for lack of time, let me skip over that. So all of this, obviously, is the work of many people. I work with two very talented research associates, Andrew Lenhardt, Rupesh Nasre, a bunch of PhD students. We have lots of visitors from many places, and if you'd like to visit us, you're more than welcome. There's our homepage, and on our website, you'll find our Galois system. So you would write your Joe program in C++, it would run on top of Linux. We also have a bunch of these benchmarks written in this data-centric style that run on this system. We call those the Lone Star benchmarks, and so you can download those as well. And then we also have those GPU implementations that I talked about, and you can download those also. And so here is my last slide, Eric. So conclusions. So yesterday, today, and tomorrow. So yesterday, the way we thought about parallelism was this computation-centric view. We looked for loops that we could parallelize, et cetera, et cetera. What I want you to think about is this different data-centric way of thinking about parallelism, where you think about the algorithm itself in terms of an operator that's performing these updates at active elements in your data structures, and then there is some schedule in which you do them. And then underlying that is your Stephanie code, these parallel data structures. And so this permits a unified view of parallelism and locality in all kinds of algorithms. And as I've shown you, you can actually build a system and get good speed-ups for many of these very complicated applications that we didn't really know how to program in a systematic way before that. And so the motto then is parallel program equals operator plus schedule plus parallel data structure. Thank you.
Great, thanks. The Lone Star benchmarks, eh? It looks like you've been settled in Texas.
Yes,
really well,
that's right.
Any questions? Yes, safe.
So my name is Saif Haridi, KTH on SICS. I'd like to ask a general question and then a more specific question about your system. So the way your model is somehow also similar to the trend that is happening in programming models or for data-intensive computing. I mean, I'm thinking of systems like Spark from Berkeley, which is like the data is like the basis, and then you apply operations and you can maybe iterate in this operation. So maybe you can comment on that and what is the perspective of your system to handle big data? I mean, which I think could be very reasonable.
Yeah, that's right. Okay, so the way that we think about our model is in terms of a generalization of data parallelism. So most of the systems that you talked about, they are trying to exploit data parallelism. And in data parallelism, essentially, you're given a set or a sequence or something, and then you're applying an operation like a map on top to that, to the individual elements, right?
Some aggregation.
That's right. And then doing a reduction. So map reduce essentially works in that style, right? So that's classic data parallelism. The difference with our system, or the amorphous data parallel model, is that in amorphous data parallelism, you're allowed to update the underlying data structure itself. So that's a notion that doesn't really exist when you're doing maps, because that's really a sort of a functional operation where you take one set of data and you produce another set of data. Furthermore, you don't have to apply your function to all the elements of that set or sequence. So in Delaunay mesh refinement, there are only some triangles that are active. You don't apply it everywhere. But you have to detect those, because then that gives you the work efficiency, right? Because otherwise you're applying it everywhere, but it's useful only in a few places. So there are lots of differences, but it's a generalization of data parallelism.
But still, what is the prospect then of having it running on terabytes of graph that is very big?
That's right. So I think that's where this data-centric approach actually helps you. Because what we've done is we've also implemented an out-of-core implementation of many of these algorithms. And so the way you think about it is very similar to partitioning this big data structure. You bring in a partition, you work on all the active nodes in that particular partition. And then if there are any edges that cross from one partition to another, you have to remember what updates you want to make, and then you apply them when you bring in the next partition. So we've actually been able to automate out-of-core algorithm generation using this data-centric approach. And that's one way that I would approach this terabytes of data problem. Sure.
So I'm Carl Philip Faxén from SICS. I want to ask about the interplay between work efficiency and parallelism when you construct the schedules. Have you... do you have to trade that off? What's your experience in trading these off when you construct the schedules?
Right. So you absolutely have to trade off work efficiency with parallelism. So this is something that came as a surprise to us, because in the more conventional HPC programs, you don't really see very much of that, right? So the amount of work that you do in matrix multiplies off n cubed, regardless of the schedule that you use. Whereas in these graph analytics applications, and also more generally these irregular applications, the work efficiency can depend dramatically. It can be asymptotically different between different schedules. And so coming up with the right schedules is actually the essence of getting work efficiency. Now, how do you automate that? There is no automatic way of doing it. So what we have is an auto-tuner where you can specify. In our system, you can specify the schedule using a simple DSL that we give you for composing schedules, and you can build very complicated schedules out of that. So all of the numbers that I showed you were obtained by essentially playing around with different possibilities, knowing some insight from the algorithm. So this is where Joe has to be a little smart. So coming up with the right schedule is not the easiest thing on earth, but you have to have some domain insight. And so when I say a Joe programmer, what I mean is somebody who's not writing explicitly parallel code. He's not a parallel expert, but he's a domain expert, knows something about the algorithm, and has enough insight to be able to come up with these schedules. And so we also have these auto-tuners that can just go through different schedules and find which one is best. But finding a good schedule is absolutely critical for work efficiency. And there is a trade-off between parallelism and work efficiency. And so it's sort of like that. So you have to find that golden mean.
Zoran Radovic from Oracle Corporation. So I think we have about 20,000 Joes, right, in Oracle writing applications every day, and our answer is to move all of these developers to Java currently. So are you looking at expanding the framework, enabling Java for Oracle developers or anybody else using Java?
So we've actually gone the other way. So our first implementation was in Java, and then we've now moved to C++. So from your perspective, it's probably a step backward, but here is the problem that we ran into. We found that it was very hard to understand performance when you have concurrent Java programs. And that's because there's so much that's done automatically for you that when you get bad performance, you have absolutely no clue about what to do. And it turns out that in order to get the kind of numbers that I'm showing you, you have to be very smart about storage allocation. Because it turns out storage allocation can become a huge bottleneck unless you do it very cleverly. And in Java, you don't have any control over that. So we went to C++ simply so that we had complete control over where allocations happen. The application programmers don't see it. That's all done within the runtime system. So we use our own allocators, in fact, and that's how we get this kind of performance. When we had Java programs, we really didn't get very good scaling for any of these applications. And so we went the other way. Now, what we could do, now that we understand what it takes to get this kind of performance, is now to go back and talk to Java implementers and say, look, here is how you should do your storage allocators. Here's the kind of control that you need to give application programmers and so on and so forth. And I'd be happy to work with you if you want to do that.
Excellent. So one last question.
Hi, there is a pillar here. You couldn't see me. My name is Ananya. I come from KTH. So I was thinking that this inverted pyramid that you showed,
yes,
where you have average Joes and Stephanies, it might not be sustainable. So my main question is, how do you let the average Joe programmers choose the different parallel data structures? Because you take away the problem of exposing parallelism, but then you expose one problem of choosing the right data structures or composability, basically.
Yeah,
right? So
that's right.
This is
yeah, so that is something that the Joe has to do, right? And the way we do it currently is we give you a bunch of different graph applications, different work set or task bag application implementations and so on, and then you simply have to select one of those, okay? And what you can do is to play around with different ones and see which one gives you the best performance. Now, is that can you improve on that? Well, if you could somehow automate that, that would be even better, but we don't know how to automate that yet, okay? Now, having said that, I think choosing a parallel data structure, right, given a menu of 5 or 6 of them for a data structure is a lot easier than having to go and implement it yourself, okay? It turns out even implementing just a simple bag, right? So a bag, you have put and get. Put a task in there, put an active element in there, get an active element out. That's all you need to do in order to have this work set, right? But doing that in a scalable way so that that doesn't become the bottleneck. If you just put a lock, acquire the lock, you're dead. And that's because each of these tasks, these activities, is very, very fine-grained. There are a few hundred instructions at most. And so you need to implement that in a very clever way. And there's a lot of code and a lot of ingenuity that has gone into just implementing a parallel bag just to maintain the task set. Okay? So that's not something that ordinary programmers or even heroic programmers can do. There are very few people in the world who know memory models and all those sorts of things at the level of detail that it takes to implement those parallel data structures. So I don't think Joe programmers will ever be able to do that. But right now in our system, you do need to be able to select some data structures and say, I want to try it out with this implementation of a bag and this implementation of a graph. And you have to play with that till you're satisfied with the performance. So if you want to automate even further, that's a great research problem. And if you want to work on it, I'd be very happy.
Okay. So we're cutting the questions there. Thank you so much.
Okay. Thank you.
So once more, here's the schedule.